Good afternoon, ladies and gentlemen. Thank you for your kind introduction. My name is Bartosz Piatek. I know this is quite difficult because of this Polish letter, but thank you. Today I'd like to present the paper entitled Fatigue Performance of Real-Scale Precast GFRP Reinforced Lightweight Concrete Arches. I would like to briefly present our work in this topic, which were conducted within the project entitled Innovative Precast Arch Elements with Increased Durability for Infrastructure, which we carried out with one of Polish company, which was interested to introduce such structures in practice. So the idea of the project was to join the advantages of lightweight concrete and GFRP rebars and implement these both materials to build precast arch elements for small span road bridges. And thanks to that, increase their durability and reduce weight, and due to that, transportation and maintenance costs. The research program included 3 real-scale test models of precast arch elements. The arches were 10 meters long, 1 meter wide, and 2.4 meters high. The depth of the cross-section was 28 centimeters. And the first reference model was made of normal weight concrete and steel reinforcement. It is called NWC steel here in this presentation, and it was subjected to both static and fatigue loading. The next 2 models were made of lightweight concrete reinforced with GFRP rebars. One of them was tested under static load, and the second one, named with the last letter F, was tested under fatigue load. During this presentation, I would like to focus on the last element and to compare it with the first reference model. This first model, made of normal weight concrete and steel, was reinforced with 60 millimeters diameter reinforcement as a bottom reinforcement and 12 millimeters as a top reinforcement. And both lightweight concrete GFRP models were reinforced with 8 millimeters diameter reinforcement for longitudinal bottom-top reinforcement and as stirrups also. Both elements were designed to have similar static load carrying capacity, these models were tested under 3-point bending scheme. They were fixed at both ends in vertical and horizontal direction, but the rotations were not blocked near the supports. Similar supports conditions are used for practical applications, so we tried to do the same in the lab. The load was applied in midspan using hydraulic actuator with the maximum static load of 630 kilonewtons, and the maximum load of fatigue was 120. The fatigue load was applied in sinusoidal viable manner with the frequency of 1.5 hertz, and the ratio between minimum and maximum load was 0.1, so the minimum load was 12 kilonewtons when the maximum was 120. For each sequence of fatigue, so after each sequence of fatigue load, we break the fatigue load and make some cycles of static load to observe changes after each part of the fatigue load. Here you can see the view of the models at the testing stand at our lab. During the test, the vertical and horizontal displacement were measured in three points. In the midspan, in the 1/6 of the span length, and near the supports. We measured also strains of rebars and of concrete, and controlled the rotation angles to assess if this static scheme considered in the calculation was stable. Here are some photos of instrumentations and gauges to measure displacement. We use LVDTs to measure concrete and strain rebars. We used foil strain gauges, and for rotation angles we used inclinometers. Just a brief description of the main results of static tests at the beginning. The lightweight concrete GFRP model exhibited much lower stiffness than normal weight concrete steel model. The deflection measured in midspan of both specimens during static loading were higher for this lightweight concrete GFRP model. Also, crack numbers and widths measured under subsequent loading steps were greater in the case of this element. And the ultimate load carrying capacity of normal weight concrete steel model could not be reached in our lab, because the maximum force which we can apply using this actuator was exactly 630. So it should be considered as a minimum load carrying capacity in this case. And the load carrying capacity of lightweight concrete GFRP model was 320, and this value was similar to the value when normal weight concrete steel model was started to yielding. So as it was expected after the calculations. After steel yielding in this first model, we can observe also some post-yielding phase of work, which is of course not exist in case of the second model. Here we can see subsequent stages of failure mode of lightweight concrete GFRP model, which was loaded statically. It failed due to shear in the midspan near the point when load was applied. So the concrete cover was detached, and we could observe final failure. What is maybe interested, up to the end of the failure, the longitudinal bars were not ruptured, so it was caused by due to shear. And now I would like to present the main results from fatigue tests. Starting from displacements, we can see also that the stiffness of the lightweight concrete GFRP model was significantly lower than in case of normal weight concrete steel model. In this first case, after 2 million cycles, we had an increase of measured displacement around 5% only, while in case of lightweight concrete GFRP models, after 250 K cycles, the increase of displacement was over 50%, and after next 40 K cycles, we observed a significant damage, and then these displacements were over 5 times greater than at the beginning. The degradation of stiffness was also visible by the increase of crack width recorded in subsequent stages of the test. In case of normal weight concrete steel model, we didn't observe any significant increase of crack width during the fatigue test, while as you can see here, in case of the second model, we observed a significant increase from the beginning of the loading before fatigue load, and during the fatigue load we observed a huge increase in this value. On these plots we can compare strain amplitudes of rebars and concrete. In case of normal weight concrete steel arch, we can see a comparison between first 100 cycles and the last first 100 cycles and the last 100 cycles after 2 million fatigue loads. While in the case of the second model, lightweight concrete GFRP, the comparison was done after 100,000 cycles. So again, we can see that the increase in strains of the rebars and concrete in this first model was slight, but even though that the comparison was after full cyclic load, 2 million cycles, but here in this model we observed much higher increase after only 100,000 cycles. In further steps of the loading, the comparison was not possible because of some gauges were broken. And the summary of the results from fatigue tests, as it can be seen here in the tables, lightweight concrete GFRP arch exhibited displacement and strain in all measured points much higher than when it comes to the normal weight concrete steel model. The values were 2 to 12, even 12 times higher. And the main difference was that the normal weight concrete wasn't failed after 2 million cycles, while the lightweight concrete model reinforced with GFRP rebars failed after 390,000 cycles. Here we can see subsequent steps of failure of this lightweight GFRP model. After 290,000 cycles, there was initiation of crack in the midspan. Actually, the crack exists from the beginning, but after this amount of cycles, it reached significant width. And after next 100,000 cycles, we observed a big crack in the 1/6 of span. And due to further increase of the displacement, we couldn't continue fatigue load, so we stopped it, and we destroyed finally this model under static load condition. Here you can see the last step of the test under static load. There was accelerated, and now the failure of the element. Summing up, the lightweight concrete GFRP arches exhibited lower stiffness, lower load carrying capacity, and fatigue resistance than a normal weight concrete steel arch. Under static load, the lightweight concrete GFRP arch failed due to shear, so its load carrying capacity could be improved by increasing this shear reinforcement. And the lower fatigue resistant of lightweight concrete GFRP arch was caused mainly due to faster degradation of lightweight concrete and also lower stiffness of the whole element due to using GFRP rebars in this case. Despite of that, ultimate load carrying capacity of lightweight concrete GFRP model was approximately 2.5 to 3 times higher than the estimated design load for a road bridge made of an arch element. So we consider it as sufficient value to apply this element in practice. Moreover, the loading scheme used in the lab was really unfavorable. So because in reality, in practice, we have distributed load along the arch instead of a point load in the midspan. So it can be concluded, in my opinion, that the lightweight concrete arch elements with GFRP rebars can stand a good alternative for small-scale road bridges. But further research on fatigue behavior on such elements are needed to establish proper design guidelines at first, and because now we have a lack of such guidelines for lightweight concrete structures with composite reinforcement, and that's it. I would like to thank you very much for your attention.